Hello, differential equation students. So in this video, let's take a look at how do we solve exact differential equations. So in the previous video, we looked at, what does it mean to be a differential equation? What does it mean to be an exact differential equation? And then we looked at some partial derivatives. We also looked at, total derivatives. And then what does it mean to be, if you have a curve, what is a differential equation for which this curve will be a solution and so on. We also looked at, how to verify whether it's an exact or not. We have two examples. Now, in this video, in this part, we will solve how do we solve an exact differential equation. So the idea of solving this exact differential equation is the following. So here you have a curve, in this case a circle, and we found the differential equation for which this will be a solution. And this reverse process is the basically the exact differential equation idea. So what do I mean by that? So if you have a differential equation, we are hoping that what if this part, the something with respect to the dx, the coefficient of dx, what if it was this, and what if this part, the coefficient of dy, happens to be this? Then we know this is same as that, right? Then we know this is same as that, and therefore we know then if you have an equation, if you have a zero on that side, that is going to be equal to something like this. That is going to be equal to something like this. Right? And so therefore now I can do an integration, and now I can do the reverse process just like we did over here, right? Just like we did over here, we can do the reverse process. And when we do the reverse process, what do we get as? We're going to get we're going to get f of xy is equal to c, and that's a solution. So the idea here is we are hoping whenever you have, you're hoping that whenever you have m dx plus n dy equal to 0, right? Whenever you have that, you're hoping that, let me, hold on. So whenever we have that, we're hoping, what if this was fx? Partial of f with respect to x dx. And what if this was fy? And by the way, I don't have to tell you, I think as I have shown before, you can rewrite this as, fx dx, and you can rewrite this as fy dy. So this is the total derivative, right? Right? So then if that happens, then, then I can say this part can be simplified into this, and therefore since it's a zero can be written like this, so then I'll have a solution to this, right? So that's the idea behind that. So when would that happen? And here's where we're going to use the here is where we are going to use the idea of the derivative. And what is the idea of the derivative? The idea of the partial derivative is that for a function to be continuous, for a function to be a nice function, and continuous, for a function to be continuously differentiable, the following must happen. And what is that following must happen? That following is this right here, which is the second mixed partial. What do we call the partial derivative of, f with respect to xy, not that one, x and y, right, should be same as partial of f with respect to y and x. What do I mean by that? So it doesn't matter which order you do the second derivative. It doesn't matter which order you do the second derivative of f, whether you do it with respect to x first and then y, or you do it with respect to y first and then x. It doesn't matter which order you do. These two have to be exactly one and the same. In other words, what does it mean is it means that in a simple form, what do we mean by that is we want this fxy should be same as fyx. So in our purposes, right, suppose if the differential equation which is in the form happens to be, this dx fy dy, fx dx fy dy, right? Suppose if it came from the same function, right, then you would have this. And so then these two, since it came from the same function, we assume that it's continuously differentiable, then the partial of this with respect to y. That's why we say, my. The partial of this with respect to y, right, is if you call this is the m, right, and if you call this is the n, then partial of this with respect to partial of this. Let me clean up a few things in here. Partial of this, use a different color. So then this, mx, my, right, should be equal to nx, because m is your fx, and with respect to y, and n is your fy, and that is with respect to x, and you're going to have fxy equal to fyx, right? So the idea here, the core concept here is, suppose we're hoping a differential equation which is of the form, right, whose m is a partial derivative of one function with respect to x, whose n is also a partial derivative of that same function. The key is the same function with respect to y. If that happens, if that were to happen, that's what we're verifying whether it's exact or not, right? Then since these two came from exactly the same function, right? Then I can do this, and here's my solution right there, right? Then I can do this, and here's my solution right there. And that is the idea in solving this exact differential equation. The question is whether these m and n, the coefficients of x and y, did it come from the exact same function? It did, did those two, did those two came from same function or not? If it came from the same function, how do we know that? Then this has to be satisfied. If my is equal to nx, then it must be that this m is a partial of f with respect to x, and this n is a partial of f with respect to y for the same exact function f, right? So that's the idea that we're going to use it to solve it. All right, so that's the theoretical part. Let's take a look at how do we solve it. Before we solve it, I also want to say one other thing. I want to share one other thing so that you can kind of easily follow me what I'm going to do. You all know this, right? You all know this very well. That if I have a function, let's just say x squared, and I do the derivative, if I find the derivative, you know that it's 2x, and when I find the antiderivative, or when I integrate this, right, when I integrate this, you know that you get x squared, right? Or you can just say no, x squared plus c. If I have x squared plus 1, if I do the derivative, that's going to be 2x. When I do the antiderivative or integral, let me just put a symbol in here so it's easy for you to follow. If I do the integration, right, of 2x, and then, this is also going to be x squared plus c. If I have x squared plus 20, still the same thing. If you do the derivative, it's going to be 2x. If you do the integration, it's going to be x squared plus c. So we have some issue here. So if I do the reverse process, ladies and gentlemen, when I do the derivative to the antiderivative, I lose something in here. What do I lose here? I don't know here what it was. If someone gives you, right? Doing this reverse, you have a function, you do the derivative and you do the antiderivative, you get this. Now from here, you don't know whether you started with this, whether you started, with this or this or this. We don't know that, right? So that's why, we say this is C is an arbitrary constant. That's how, when you do go from derivative to the antiderivative, we get this arbitrary constants. Now, when we deal with the partial fractions, there are some similar issues. So what do I mean by that? So let's take a look at this function, x squared plus y. As simple as that, right? Let me do the partial of f with respect to x. Let me do the partial of f with respect to x. Then this is going to be 2x. If I integrate this, right, with respect to x, I am going to have x squared, right? Now I cannot say it's a constant. Actually, what I missed it, since because of the partial derivative, what I missed it, it's not a constant, it's rather a function of x. Now I have an arbitrary, I no longer have arbitrary constant. Now I have arbitrary functions when I deal with partial derivatives, right? Now I have to deal with arbitrary functions when I deal with partial derivatives. It depends on what variable you have. So similarly, for example, let's just take a look at this one. I have, let's just say, I have x cubed plus e to the y times sine x, right? Let me do the fx. When I do the fx, again, this is 3x squared. When I do the derivative of that with respect to x, when I do the integration of this with respect to x, I'm going to have, simply x cubed. I'm missing something in here. Then what I'm missing here is, oh, I made a mistake. I meant to say this is sine y, by the way. This is sine y, by the way. We'll do the sine x in the next one. So then here I'm missing something. Whatever that I'm missing, I'm going to call c of y. Now let's take a look at this one. X cubed plus e to the y sine x, right? When I do the partial derivative of this with respect to x, I am going to have 3x squared plus e to the y cosine x, right? And now if I do the integration of this, right, with respect to x, so I have 3x squared plus e to the y cosine y. And by the way, for those who have not have done extensive with respect to the partial integration, this is very simple, the same way that you did before. If you have a variable, sorry, I'm doing this with respect to x, right? If you have a different variable, you can treat them as a constant, right? You can treat them as a constant. That's how you do that one. So when I do that, what happens, right? When I do that, what's going to happen is I'm going to have, here is a 3x squared with respect to x. So that's a variable of integration. So this is going to be x cubed. Then plus e to the y, but this is x in here. So that's nothing to do with the variable of integration. So I'm going to treat it as a constant. So I'm going to have e to the y. But I made a mistake in here. Again, there is a typo. So many typos. This was supposed to be x, right? But then that's a cosine x is actually, as a matter of fact, that's a function of x, right? Cosine x is a function of x. And so therefore, what you're going to have is you have to integrate it. If you integrate it, it's going to be sine x, right? And then now you cannot say plus c. Here you're going to say again function of x in here, function of y in here, right? Although in this case that happens to be a 0, that's okay, but still it could be a function of y. So when we go from the derivative to the antiderivative, the derivative antiderivative process, you get arbitrary constants. When you work with partial derivatives and then you do the process, you have arbitrary functions. Again, this was with respect to all that you do is with respect to x. If you do this with respect to y, then you're going to have arbitrary functions of x. Let me give you a couple of examples. Suppose I have this function, let's just say f of x comma y, which is x squared plus y cubed. and you do the derivative with respect to y, fy, which is 3y squared. And if you integrate this with respect to, y, right, then you're going to have simply y cubed. So you're missing something. So whatever you're missing is actually what I'm going to call a function of x, right? I'm going to call g, but you can see c or g, whatever that is, it doesn't matter, right? So that's what we have. Now this is your arbitrary function of x. Let's take a look at another one. Let's just say I have this function f1. Let's call this is f2 of x comma y, which is x squared cosine x, ln of tan inverse of x, right? Plus y. Now, if I do the derivative of this, right? If I do f2y, if you do the derivative of f with respect to y, I should say f1 of y here, by the way, right? Then what I'm going to have is I'm going to have this is all a function of x, right? Although it's very complicated, I don't have to worry about it, right? I'm just going to simply say it's 1. And if I do the integration of 1 with respect to y, and this is going to give me simply y. So now I'm going to say plus something is missing, and that missing is, as a matter of fact, g of x, right? So that's how, when you do the partial derivatives, now you have arbitrary functions, and that is important in solving this exact differential equation. So let's see, how do we solve this exact differential equations? Let me go through the general idea, and then we will see how do we work it out with this particular example. So now, generally, the equation that you're going to have is you're going to have m dx, m of x comma y dx plus n x comma y dy equals 0. That's all you have. So, for my simplification purpose, I'm going to say this is, m dx plus n dy equal to 0. Right? Now, suppose, as we said earlier, as we said over here in this area, suppose we are hoping, right, that hopefully this m and this n came from the same exact function f in such a way that looks like this m is your fx and this n is your fy, right? This n is your fy. So we are hoping that. How do you know that our hope is right? That's one, we do the step number 1, and that step number 1 is we verify whether it is exact or not. So we verify. What do I mean by we verify? So we're going to take a look at the m and then find the derivative with respect to y, and we're going to take a look at the n, find the derivative of that with respect to y, with respect to x, and see if they are equal. If these two are equal, then this is exact. If these two are equal, then this is exact. If it's not equal, then it doesn't work. You got to do some other method, right? All right. Now, if that is exact, ladies and gentlemen, as I said, then this m is your fx, and then this is, n is your fy. So therefore, now I have the right to rewrite this as this one. So, I can rewrite this as fx dx plus fy dy, and that, by the way, is equal to 0. And by the way, that means what? That means this is, d of f of x, y, or d of f, if you want to say, df is equal to 0, right? Now, this is fx, right? So let me go back to what I just did here. So now you have your fx, just like we did over here. To get the f, what am I supposed to do? I'm supposed to, if I integrate this with respect to x, that's going to give me my the original function f, right? If my f of x is this, if this was fy, If I do the integral of this with respect to y, then I get my original f back, right? Then I get my original f back. The only problem is we might lose something in the process, but we'll figure that out. How do I do it in a moment, right? We can figure that out. So what I am going to do, I can choose either one, but I think for the sake of simplicity, let's just say to find the original function, this f. To find this original function, this f, what I am going to do is I am going to take a look at the fx. So that's my second step. I'm going to take a look at my fx, and I'm going to integrate this with respect to x. You don't have to do that. You can also take a look at the fy and do this with respect to y, and that's perfectly all right as well. Sometimes that might be easier, right? It depends on the computation sometimes, and that's perfectly all right. There is nothing wrong with that, right? When I do that, what's going to happen, ladies and gentlemen? Just like we did earlier here, when we did that, what happened? We got, when we did this, fx and the partial of f with respect to x, we did not get arbitrary constants. Rather, we had arbitrary function of y. So therefore, now whatever we have, we're going to call this as whatever we get, we're going to call this as f. I'm going to say f tilde, if you don't mind, or f bar is okay as well. Let's just go with the f bar. F tilde, okay, it looks fancy. F tilde of x comma y plus a function of y. I'm going to call it as a g of y. I used it g before, but here I'm going to call it as a g of y. And by the way, if you do the same thing with respect to y, then this is going to be f tilde of xy plus a function of x, right? But that's not what I'm going to do. Now, that means I got this. I got the f, right? I got this particular f right there. Now I got this f. The only problem is there is some missing component. There is a mystery component, and that mystery component is g of y. So how do I figure out this mystery or missing mystery function g, right? Then we're going to do the same. We're going to repeat because we have another thing that we haven't made use of it, right? I made use of f. I did not make fx. I did not make use of the fy. So then what I'm going to, whatever I have here, so that's your step number one. Step number two, by the way. Then what is the next step? The next step, what we are going to do, we're going to take a look at this guy right here, f tilde of x comma y with that mystery function f. We're going to take a look at this and find the derivative of that with respect to y. And by the way, what is this one? This is what we are saying. This is your f. Whatever we are saying is this one. As soon as you figure this out, that's exactly this guy right here, right? So what is this then, right? What is this then? This actually is, if you really see, that's your f of x comma y, right? With respect to y. And that, by the way, let me just move this up a little bit. And that, by the way, is equal to m, because that's fy, right? That fy. Great. Now I have an equation, right? And if you take a look at the left-hand side, ladies and gentlemen, let me just do this. So I'm going to have f tilde, not f, by the way, f tilde with respect to y, plus we find the derivative of this with respect to y. This is going to be g prime of y. That's going to be g prime of y, right? So what I have here is I have a g prime of y, and that has to be equal to, it's not m, by the way, it should be n. There should be n, excuse me, and that should be equal to n. Now you have an equation to solve for n. So the next step is to solve for g prime. So here is going to give you the g prime of y, which is going to be n minus f tilde of y. And then you find the g. What is the g? G of y is equal to integral of g prime of y dy. And that's going to give you a g, and that might have an arbitrary constant here because g is a single variable function. And then you do that. Then what do you do? Step 5. Then you write the solution as f of x comma y is equal to c, which, by the way, is your f tilde that you got, right, of x comma y from the integration, plus this new g of y that you just got here. So this is your, new g of y, right? You just plug it in over here, and this f tilde is the f tilde that you got from there. That f tilde that you got from here, not from there. I'm sorry, from here, right? That's f tilde, and this is your g of y, and that's how we would solve this exact differential equation. Let me show you how do I execute this plan with this example. Then you can kind of follow me along easily. All right, let me change the different color. All right, step number one. Let's see. Let's verify. Here, my m is equal to 2xy, and n is equal to x squared minus 1. By the way, if you really take a look, this is exactly, and I should say this is equal to 0. For some reason, I'm missing a 0 there. If you really look at this is our exact, same example one, so I don't have to worry about it. You can just copy paste it, right? This is exactly the same problem there. So you can worry about it. You don't have to worry about it. You can copy paste it. So we know that that's exact, right? So just in case, my, which is 2x, is also equal to ny. Therefore, this is exact DE. Done. Now, in this case, I'm going to take a look at the m. I'm not going to take a look at the n. So the step two, what I'm going to do, I'm going to take a look at the m, which is fx, by the way, right? So this is also, if you want to write it, this is same as saying integral of, m dx. So I have my m here, which is equal to 2xy. I'm going to take a look at the m, which is 2xy. And I'm going to find the derivative of that. I'm going to integrate that with respect to y. When I do that, integrate this with respect to x, because this is fx, right? So this is going to be with respect to x. And when I do that, I'm going to treat my y as if it's a constant. So all I have here is integrating 2x with respect to x. When I do that, you all agree that this is going to be y is a constant. I'm just going to remain as is outside. If I integrate the 2x, I'm going to have x squared, 2x squared over 2, which is x squared, and that's all. Now, rather than a c, since I did the integration with respect to x, rather than a c, now I'm going to call this is, let me use a different color. I'm going to call this is a new function. I'm going to call this the g of y. Right, that's a step number 2, as I just started right here. And this is what I mean by the f tilde of xy, right? This f tilde of xy is this right here, right? And here's your g of y, and that's right there. That's your g of y. Now, what's the next step? We're going to take a look at this entire thing and find the derivative of this with respect to y, as we just shown over here, right? And if I do that, that's my next step. I'm going to take a look at the x squared y plus g of y, and I'm going to find the derivative of that with respect to y, and I'm going to set it equal to n. When I do that, you would agree with me that I have my left hand side is going to be simply x squared, and then plus g of y is going to be g prime of y, which is equal to my n right here is, here is my n right there, x squared minus 1. If you bring it out over here, what I'm going to have is I am going to have x squared minus 1. And now if I solve for g prime, now if I solve for g prime, I am going to have my g prime of y is going to be, it's a very simple problem right away. As you see here, I can cancel these and these two together. When I do that, I'm left with minus 1. So my g prime of y is minus 1. The step 4 is, finding the g of y. The g of y is simple in here, which is integral of negative 1 dy, which is negative y. You can just leave it like that. You don't have to worry about, plus c, because we're going to have a c anyway. If you really see, we have already a c right there already. So therefore, my f of x comma y, the one that I was hoping is going to be f tilde, which is this guy right here, right? Which is x squared y plus g prime and g of y, which is this right here, right? So I'm going to say that's a minus, right? Minus, let me change the color in here so you know what it is, minus y, and that came from this right here, right? and that's your f of x comma y. So therefore, the solution, right? The solution, the way that you write the solution is going to be the solution is going to say we write it as we write the solution as the solution as, f of x comma y is equal to c, just like you see in here, right? And my f of x comma y is x squared y minus y equal to c, and that's the solution curve, right? That's the solution curve. So now what we did is, as I said earlier, we did the reverse process. If you take a look at here, this is simple, right? Given a curve, we found the differential equation. That's a very simple. What we did is now, given a differential equation, we found the curve, and that curve is this particular one. So that's the curve, right? And this is the corresponding. This is the curve, which is a solution to this corresponding differential equation. So let me quickly go through the process one more time so that you kind of follow what I'm doing. So again, what did we do? The very first step, we verify whether it is exact or not. Once you verify, you can take a look at the fx, or you can take a look at the m, which is the fx. You can take a look at the m, which is fx. And then you can do the integration of that with respect to m, or you can also take a look at the m n and then do that with respect to y, right? Anyway, in this case, we did this with respect to m, and then once you do that, now you're going to have the f tilde, what I call f tilde, and then you're going to have plus g of y. That's your arbitrary function of y instead of a constant that we used to in our calculus or on calculus 2. Then you take a look at this and find the derivative of that with respect to y, and you set it equal to n. So you're going to have something like that. When you set it equal to n, then you simplify. That's going to give you g prime of y. Then you simplify, or you solve g prime of y. Once you have the g prime of y, from the g prime of y, you solve for g. Once you have a g, now you write your f of x comma y as f tilde of x comma y plus g of y, and you set it equal to a constant, and that's going to be the solution to that particular exact differential equation. And that's how we solve the exact differential equation. Again, there are many problems. I recommend you review the homework number 5, or worksheet or homework number 5, which has many problems with the answers there. If you have any questions, you can ask me later. That's all I have. Or if you have any question, you can ask your questions on the comments. I'll be happy to answer those questions. That's all I have for now. I will see you in the next video with another method of solving differential